Alright, so in this example, we're asked once again to find where the function has increasing intervals and decreasing intervals. And then we're also asked to determine if the function has a relative maximum or a relative minimum, and we want to know at what points they occur. So the first thing that we're going to do is we're going to find the first derivative. So the first step is to find the first derivative, find our slope formula. So before we do that, we have three separate terms here, but one of them has a variable in the denominator. So I'm going to rewrite the original function. I'm going to go ahead and bring that up to the numerator. So I have not taken the derivative yet. I'm just going to go ahead and move that up, and when I do, it becomes x to the negative 1 power. And now I'm going to take the first derivative. So our first derivative, have a little mark there, f prime of x equals. So the first one, I'm just using the power rule here, so that gives me 4x. And then here I'm going to use the power rule again. Negative 1 times 4,000, that's negative 4,000. Reduce the exponent by 1, so that gives me x to the negative 2 power. The last term is a constant, and the derivative of constants is 0, so we don't have anything for that. Now, because we are going to use the first derivative, once again I'm going to rewrite it. I'm going to move this negative 2 back down to the bottom of that fraction. So we have 4x minus 4,000 divided by x squared. So when I pull that down to the bottom, back to the bottom of the fraction, the exponent becomes positive again. So this is my first derivative. So the first step is to find the first derivative. The second step we're going to do here is we're going to determine x values that make the first derivative equal 0 or make the first derivative turn out to be undefined. Alright, so we're going to do both of these things. So the first thing that I'm going to do is I'm going to take my derivative and I'm going to write it down here, and I'm going to set that equal to 0. Alright, so we're going to solve this equation. I'm going to bring one of the terms over to the right hand side, so let's just bring this negative 1 over. That'll be pretty easy. So that's 4x equals now a positive 4,000 divided by x squared on the right hand side. Now I have one fraction, let's write this as a fraction, equaling one fraction, and we can cross multiply. So that's pretty nice. I get 4,000 times 1, which is 4,000, and then I get 4x times x squared, which is 4x cubed. Alright, so now I don't have any more fractions, which is nice, and now I'm going to solve for x. Let's get rid of the 4, so I'm going to divide both sides by 4. That gives me 1,000 is equal to x cubed. And now I just have to take the cube root of both sides. So now I get 10 is equal to x. So this is one of my numbers that I'm going to put on my number line. So remember, the third step is to write out our number line and to put our numbers on there. Alright, so before I do that, I'm going to find out also where the first derivative is undefined. So what would make my first derivative turn out to have division by 0? Well, the only way that I can have division by 0 is if I have a variable in a denominator. Okay, so that's what I'm looking for here, is when I write it out with all positive exponents, do I have a variable in the denominator? That's the question. And the answer is yes, I do. What would cause that denominator to equal 0? Well, let's set it equal to 0. X squared equals 0. Well, the only way that can happen is if I have x itself equaling 0. So I do have two numbers that I'm going to put on my number line. So my two separation values that I'm going to put in boxes. So I have 0 and I have 10. Alright, so after I have my number line, then I'm going to start to choose some test values in between around all of these values. So I'm going to choose the easiest ones that I can. So what's to the left of 0? Something smaller than 0, well, that would be negative 1. Something in between 0 and 10. Now you can choose anything you want to, but I try to keep my numbers as small and as easy as possible, and 1 is really nice. And then to the right of 10, I'm going to choose 11. So here are my test values. Now, we want to find out what the slope is at these points, so I am going to plug into the first derivative to determine the slope. So if I put negative 1 into the first derivative, so remember the first derivative is right here, we get 4 times negative 1 minus 4,000 divided by negative 1 squared. I just want to see if the slope comes back positive or negative. So this value is negative 4, and then I get minus, and this number is always going to be positive. In fact, that's a positive 1, so that's pretty easy. So I get negative 4,000 divided by a positive 1, I get negative 4,000. And this number definitely, negative 4,004, definitely a negative value. And all I care about is if that first derivative is positive or negative. And if it comes back negative, that tells me that I have a decreasing slope, or I have a negative slope. So that tells me that the graph is slanting downhill from left to right. So we're decreasing. I'll put a D there for decreasing. All right. So what happens when we put a 1 into the first derivative? What does the slope come out to be? So let's see. So now we get 4 times 1 minus 4,000 divided by 1 squared. So once again, this is going to turn out to be negative as well because we have 4 minus 4,000, and we get what? Negative 996. Definitely negative again, and if I have a negative slope, that tells me that I have the tangent line is slanting downhill from left to right again, so we're decreasing again. All right, and lastly, we're going to test 11. So if I test 11 into the first derivative, notice that for all of these, I'm trying to determine the slope. And so I always plug it into the slope formula, which is the first derivative. For all of these, I'm determining the slope. Is it positive or negative? The slope of the tangent lines, which means I have to plug into the first derivative here. Okay. All right, let's plug in 11. So I get 4 times 11 minus 4,000 divided by 11 squared. All right. I end up with 44 minus 4,000 divided by 121. I get 44 minus 33 point something something something. Don't really care about the other part. You can put it in the calculator if you want to, but definitely 44 minus 33 point anything is going to turn out to be something positive. So we end up with a positive slope, which tells us that on this particular interval from 10 on, the function is increasing. So it's going uphill from left to right. All right. Now, before we determine all of the rest of the information that we need, we want to notice something. Way back from section 2.1, we talked about the difference between asymptotes and wholes. All right. For this particular function, when I go back to the very original function, notice that we have a variable in the denominator for the original. If I have an x value in my denominator, I might have a whole or I might have an asymptote. If it cancels out with something in that fraction, then I would have a whole, but in this case, nothing is going to cancel out, so I end up with an asymptote at x equals 0. So if we want to think about kind of how we're going to define our intervals here, we have to be careful about one thing. There's an asymptote there right here at x equals 0 at one of our critical values, one of those separation values. Because there's an asymptote there, and let's just go ahead and write it here again, I can't include that as part of the intervals because there is no point on that particular x value. So in order to say that we're decreasing, we're going to separate this. So I'm going to say negative infinity all the way to 0. And then we're decreasing again from 0 all the way to 10. Okay, I'm not going to be super picky about that, but just be careful about how you define your intervals. If there's an asymptote there, then we'll write it as two separate intervals. Okay, where are we increasing? Well, we're increasing from 10 to infinity. Okay, so do we have a relative max? Do we have relative minimums? So let's look at this. X equals 0 is not a relative max or a relative min because it's not a point on the graph at all. So, but anyways, we're decreasing here, then we decrease again, so it's not even eligible because we don't switch from increasing to decreasing, decreasing to increasing. We just go down, and then we keep going down. So this is not a relative max or a relative min. But 10 is good. 10, if I plug into the original function, will come out as a point, and notice that we're decreasing and then we're increasing. So we're going downhill, and then we start going back uphill. So that puts 10 at the very bottom of that valley. So if it's at the very bottom, is it a relative max or a relative minimum? Well, a minimum means we're at the very bottom, so this is definitely a relative minimum. So we have no relative maximums. Let's go ahead and just write the word none so that that's really clear. But we do have a relative minimum, and it occurs when x equals 10, and I want to know what the y value of that point is. So how do I find that out? Well, I just plug it back to the original function because we're looking for a point on the original function where we achieve that minimum. So I'm going to plug 10 in. So that's, and I'm going to write here that I'm using the original function to find the relative maxes and mins. We always go back to the original function because we're looking for the point on the original graph. I'm going to say plus 4,000 divided by 10 plus 13. So we're going to put 10 in the original function everywhere that we saw in x. So I get 10 squared, which is 100, times 2, that's 200. And you can throw all this into your calculator. You don't have to do it by hand. That gives me 400 and then 13, up with 613. All right, so for example 4 here, we're going to do the same steps. We want to determine increasing and decreasing intervals. So we're going to find the first derivative. Okay, we have to use the chain rule here because we have a group of terms raised to a power. So we're going to bring the 2/3 out, reduce the fraction by 1, so that means I'm subtracting really 3 over 3, which gives me a negative 1/3. Alright, so remember this is the chain rule. We have a group of terms raised to a higher power. So the first step is to find the first derivative. And I'm going to go ahead and write this with only positive exponents again. So I'm going to bring the part that's raised to that negative exponent, I'm going to go ahead and bring it to the very bottom of that fraction. Okay, it just makes it, a lot easier to work with. So it becomes a positive 1/3. We're going to bring this to the bottom of the fraction. So I'm going to use this as my first derivative as I go forward. Okay, the second step we said after we find the first derivative is to determine any x values that cause the first derivative to be 0 or that cause the first derivative to be undefined. So anything that causes our denominator to be 0. So the first thing I'm going to do is I'm going to figure out if there are any x values that cause my cause my first derivative here to equal 0. So we're going to set this equal to 0. And it's a fraction set equal to 0, so we're going to think about both sides as fractions, and we're going to put that over 1 there. And I'm going to cross multiply. Now, what's really nice here, 0 times anything else is always 0. Okay, so make sure that we keep that simple. 2 times 1 is 2. We get 0 equals 2, and since we have no variable, this is from the old days there, false, no solution. So there is no place that causes our first derivative to equal 0. So no solution there. That's actually kind of nice. Now the only other thing we have to worry about is what would cause our denominator to equal 0 to give us something that comes out undefined. So we'll take that denominator that we have and we'll set it equal to 0. Alright, so this should be familiar, the idea of kind of finding, the idea we talked about finding where the function is discontinuous or where the function, the domain of the function, all of these things are kind of the same thing, finding out where the function would be undefined. So to solve this for x, we're going to divide both sides by 3. Okay, we know that raising something to the 1/3 power is the same thing as a cube root. So let's go ahead and just rewrite this really quickly as a cube root. Just kind of simplify matters. Okay, and of course if I was going to solve this equation, if I have a cube root, then I'm going to take the cube, I'm going to cube both sides. So we get x minus 3 equals 0. And pretty simply we find that if I solve for x, we get x equals positive 3. So that moves us to our number line step. We're going to take every value that we found from step 2, all those x values, and we're going to put them in a box on our number line. Alright, and then now we're going to choose test values. So let's call step 3, we can say, well, let's test values. Something to the left of 3. Okay, the easiest number I can think of that's to the left of 3, since it doesn't matter what I pick. I can pick 2, I can pick 1, I can pick anything. I'm just going to pick 0 because 0 is usually really easy to test. On the other side, I'm going to keep it small. I'm going to choose 4. So these are my test values. Now, where do we plug the test values in? To the original function or to the first derivative? Okay, the answer is the first derivative. Okay, so make sure that you're plugging into the first derivative. Remember, we're trying to find the slope. Okay, so we're trying to find the slope. What is the slope when x equals 0? What is the slope of that tangent line? So we'll plug it into the first derivative and see what we get. So I get 2 divided by 3 times 0 minus 3, cube root of that. Okay, so what do we get? Well, we definitely get a positive 2 at the top, so that's easy. At the bottom, we have 3 times negative 3 raised to the 1/3 power. The easiest way, now you can throw this into your calculator, okay? Let's just think about this as cube root again. You could throw all that into your calculator and your calculator would tell you what you get, okay? The easiest way, since we really only care about positive or negative things, the easiest way to do this is to think about it as a fraction and think about how it will reduce in the end. The top number is positive, okay? The bottom number, we have the cube root of a negative number, and the cube root of a negative number is always negative. So here's a negative. 3 is positive. So I do a positive number times a negative number, I get something negative. So the top of the fraction is always positive, the bottom of the fraction will always be negative. Overall, do we get a positive or a negative number? We get a negative value. So you can do that in your calculator to find out it's negative whatever number it is, or you could just deduce from this that it's going to be a negative number regardless of what the actual number is. All we really care about is it positive or negative. So it's decreasing, which I'm going to draw a little line here that's going downhill from left to right for the interval to the left of 3. Okay, I'm going to do the same thing here for the left value. I'm going to plug in a 4. I get 2 times 3, and then 4 minus 3 to the 1/3 power. And once again, I'm going to make this simple. Positive 2 at the top, that's all I really care about. At the bottom, I end up with 3 times a positive 1 and the cube root of that. So let's just go ahead and write that as the cube root of that. All positive values here, so the bottom number definitely turns out to be positive. Positive divided by positive is definitely positive, so we're increasing to the right. Okay, so this one turns out to be pretty simple. We just have to remember that we use the chain rule here, and that we're looking for where the first derivative is 0 and where the first derivative is undefined. We use those x values on our number line in boxes, and then we pick test values to the left and to the right of the boxes and figure out when we plug those test values into the first derivative, do we come out positive or do we come out negative? And once we know that we're decreasing if the slope comes out negative, and we're increasing if the slope comes out positive. Okay, so this is for negative outputs, and this is for the positives. Now, where are we increasing, decreasing in our relative maxes and mins? Well, this one's pretty straightforward. We are decreasing from negative infinity all the way to 3. We are increasing from 3 to infinity. So pretty nice there. Do I have a relative max or a relative minimum? And we're going downhill, and then we change to going back uphill. So let's kind of visualize that, downhill and then uphill. Definitely looks like we're at the bottom of that hill, or the bottom of the valley there, whatever you want to call it. So definitely not a maximum. The maximum means that we're at the top. We're definitely at the bottom. We start to visualize that movement of going down and then going back up. So we have a relative minimum, and it occurs when x equals 3. Now we want to know the y value for which it occurs. So if I want to know the y value of that point, then I'm going to take the 3 and I'm going to plug it back into the original function. Okay, remember that for both of these, when you're actually finding points on the original graph, then you have to use also the original function. Okay, so we're going to go back. We have f of 3, and then we're going to do 3 minus 3, and we're going to raise that to the 2/3 power. Now this is really nice because 3 minus 3 is 0, and 0 to any power is still 0, so it turns out to be a pretty simple calculation. So at the point 3 comma 0, you have that relative minimum. And one thing I do want to encourage you, once again, plug these graphs into Desmos. Put that into Desmos, and then just prove that everything that we found here algebraically also is true when you look at the graph. All right, now one thing that you have to know when you're working on the test, one thing that you have to know is you have to know when to use the quotient rule, when to use the product rule, when to use the chain rule. These are things that you just have to know. So for this particular problem, we have a fraction with variables in the numerator and denominator. So what rule are we going to use here? So if you said quotient rule, that is correct. So the quotient rule is what we use when we have a fraction. And remember what the quotient rule is. It's the denominator as is multiplied times the derivative of the numerator. So that's times 2x minus, and the negative is important there. Now it's minus the numerator as is times the derivative of the denominator. Now, pretty easy here. The derivative of that denominator is 1, so pretty easy. All of that over the original denominator, and then I'm going to raise that to the power of 2, so we're going to square it. Now, because we are going to use it, I am going to simplify this. All right. So I'm going to do a little distribution. So I'm going to do 2x multiplied into the parentheses. I get 2x squared minus 2x. And then, of course, this one's easy. I just get negative x squared all over that denominator squared. And I'm going to do one last little simplification here. 2x and then 2x squared minus x squared. Let's equal minus 1x squared. If I combine these like terms, I just get x squared. And then my minus 2x is going to come down. Okay, so this is my first derivative that I am going to work with. Okay, so there's our first derivative. Remember, the first step is to find the first derivative. The second step is to set the first derivative equal to 0. We're going to find out what x values cause that to happen, and to find out what makes the first derivative undefined. So what x values would cause these two things to happen. All right, so let's do this. First derivative, set it equal to 0. All right. We're going to think about both sides as fractions, and then I'm going to cross multiply. So I get 0 times this is 0. This times 1 is this itself again. All right, and I'm solving a quadratic equation. I'm going to try factoring here. My greatest common factor is x, and that leaves me with x minus 2. In the parentheses, remember you can always multiply it back in to make sure you did it correctly. And then we're going to set each of those factors equal to 0. So I get x equals 0 as one of my separation values that I'm going to put in a box on my number line. And I'll also get x is equal to 2. All right, so we know that the next step here, we're going to make our number line. Step 3. Now, before we do that, of course, we do want to make sure that we have all of our values on there, including what would make our first derivative undefined. So in order to do that, remember that we're looking for division by 0. So is there an x value that would cause the denominator to be 0? So all we have to do is take our denominator, set it equal to 0. So we're taking the denominator of the original first derivative there, and we're going to set that equal to 0. And this one's pretty easy to solve. We're just going to take the square root of both sides, and I get x minus 1 equals 0. And that gives me x equals 1. So 1 would cause our first derivative to equal be undefined, because it would cause that denominator in the first derivative to equal 0. All right. So we have 3 separation values. We have 0, put that in a box. We have 1, and we have 2. Okay, so this was a little bit more interesting because we don't get to choose super nice numbers, but our test values will turn out to be some fractions and decimals, and we'll just use decimals instead of fractions. That'll be fine. I'm going to choose something to the left of 0. I'm going to choose negative 1 as my test value. And between 0 and 1, I'm going to choose 0.5, or a half. And I'm going to choose 1.5 to be in between 1 and 2. And on the other side of 2, I'm going to choose a nice number. I'm going to choose 3. So we do have a few things that we want to test. Now, once again, do we plug into the first derivative, or do we plug into the original function? Well, you have to ask yourself, what are we trying to find? We're trying to find the slopes of the tangent lines. So that's important. Where's our slope formula? Our slope formula is the first derivative. So when you're testing your values out, you're plugging them into the first derivative. We're going to simplify this a little bit. Or we can simplify it a little bit, or you can leave it kind of as is. So let's see. I can take my negative 1 and I can plug it right into my first derivative. All right. Now, one thing to simplify it, the denominator. Let's think about the denominator for a minute. The denominator is x minus 1, and the last thing we do in the denominator is we square it. What is that going to make it always? Right? The denominator will always be positive, right? So you always take the number, put it in, and then the last thing you do is you square it. So it always turns out to be something positive. So I'm not going to even do the calculation. The denominator is positive. Now the top, we have to do a little bit of calculation. Negative 1 squared is positive 1. Negative 2 times 1 is a positive 2. So we end up with 3 over something positive. But ultimately, what do we end up with? We end up with something positive divided by something positive. So definitely end up with something positive. So on this interval, that tells me that the interval is increasing. So our slope is positive. So we think about a line with a positive slope kind of going up. So uphill from left to right. Increasing there. We can plug in 0.5 and we'll find out the same thing. So 0.5 squared minus 2 times a... And our denominator, once again, last thing we do is square it, so our denominator, once again, will always turn out to be positive. So we really don't even have to do any work, once again, for the denominator. You can put it in your calculator if you want to, just to prove it, but since you're taking the number on the inside of the parentheses and squaring it, you always end up with something positive. Now the top, what do we get for that? 0.5 squared minus 2 times 0.5. Just throw that into your calculator, basically as you see it. If you want, you end up with something that turns out to be negative there. A negative number at the top divided by a positive number, we end up with negative. If our slope is negative, then that tells us that we're decreasing. So we're going downhill from left to right. We're going to do the same thing with 1.5. Now this time I'm just going to say that the denominator is positive, so I'm not going to worry about that, because we already know that's going to be positive for every single one of them. So we're going to do 1.5 in our calculator, square it, minus 2 times 1.5. And when you put that into your calculator, you should get something negative again. So we have a negative number on the top, positive number at the bottom, which tells me overall negative divided by a positive number would be something negative. So we're decreasing again. So we're going downhill. And then the last number that we're going to test is a positive 3. So we get 3 squared minus 2 times 3 all over. Once again, we know the denominator will be positive no matter what, so I'm just going to put plus there. So at the top we end up with 9 minus 6, which is definitely a positive number, divided by a positive, so we end up with a positive slope, which tells us that we are increasing as we go from left to right. So we're going to put a line pointing up from left to right. So we're increasing, decreasing, decreasing, and then increasing again. Alright, so we have a lot of information here. Before we actually go and write our intervals of increasing and decreasing, it looks like we're decreasing from 0 to 2, but one thing we want to be careful about is, can we lump the intervals together? And before I do that, I'm going to see if 1 is actually an asymptote or a whole, or if it's actually just included in the function. So if I go back to the original function, you notice that if I plug a 1 in, if I plug that x value of 1 in, what does it do to my denominator? It causes it to be 0. So that tells me that at this particular point on the graph that there's an asymptote. So I am not going to lump them together. I'm going to leave them separate. So I'm going to say that we're decreasing from 0 to 1, and then we are decreasing again from 1 to 2. Now, I'm not going to be super picky about that, like I said, but something to be careful about and watch out for. Technically, you would write them as 2 separate intervals there. All right. Where are we increasing? And those are pretty easy. We're not going to lump those together because they're not touching at all. So we're increasing from negative infinity all the way to 0. And then we're also increasing again from 2 to infinity. All right, so do we have any relative maxes or relative mins? It looks like we're going uphill. So we're going up, and then we switch to going down. So this would tell me that x equals 0 is a relative max, because we're going to be at the top of the hill. x equals 1 is not a relative max or a min. For one thing, it's an asymptote, so it's not a point on the graph. But you notice that we're going downhill and then we're going downhill again, so that would not lead us to a relative max or a relative min. But at x equals 2, this number, the last number here in the box, we're going downhill and then we switch to going back uphill. So this would tell me that at x equals 2, we have a relative minimum. So just think about the way that the graph would be moving to decide which one would be relative max or relative min. So a relative max occurs at x equals 0. The relative min occurs at x equals 2. And we can find those values, those y values, really simply and easily. And remember that when we find these two, we plug into the original function. So this one's actually going to be really nice. The original function is super easy. Plug in a 0. That's 0 squared divided by 0 minus 1. We end up with 0 divided by minus 1, which is 0. So that's pretty nice. And then we'll do the same thing with 2. Really easy. We end up with 2 squared divided by 2 minus 1. That's 4 over 1, so we end up with 4. So our relative max and relative min, we plug into the original function to find those original points on the graph. We find both the x and the y value of those points.